A single teaspoon of this star would weigh more than every human being on Earth, combined. It is the densest object you can actually stand near without it becoming a black hole. And here is the strange part. We have measured its size, its spin, its weight, and we still do not know what sits at its very center. Tonight, the honest answer to what's really inside a neutron star. Start with something true and impossible at the same time. Take a star far heavier than our Sun. Let it run out of fuel. In its final second, its core collapses so hard that protons and electrons are crushed together into neutrons, and a piece of space about 20 kilometers wide is left holding more mass than the Sun. That object is a neutron star. We did not guess this into existence. In 1967, a graduate student named Jocelyn Bell Burnell noticed a radio signal pulsing with almost impossible regularity, once every 1.3 seconds, like a cosmic metronome. For a moment, the team half-jokingly labeled it "Little Green Men." It was not aliens. It was a neutron star, spinning, sweeping a beam of radiation past Earth like a lighthouse. We call those pulsars. We have now found thousands. So let's be precise about how strange this thing is. A neutron star packs roughly 1.5 times the mass of the Sun into a ball the size of a city. The gravity at its surface is around 200 billion times stronger than Earth's. If you could somehow stand on it, you would not stand. You would be smeared into a layer a single atom thick instantly. The surface may be a crystalline crust of iron under unimaginable pressure, and it spins. The collapse takes a slow, wide star and winds it up like a figure skater pulling in her arms. Some neutron stars rotate hundreds of times every second. There is one pulsar that spins 716 times per second. Its equator is moving at nearly a quarter of the speed of light. Think about that the next time a day feels long. Now the magnetism. When the core collapses, it concentrates the star's magnetic field to a level that breaks the imagination. The strongest magnets we build on Earth are measured in tens of Tesla. A class of neutron star called a magnetar carries a field of around 100 billion Tesla. If a magnetar passed between us and the Moon, its field would wipe the data off every credit card on the planet. And that is the gentlest thing it would do. Get within 1,000 kilometers, and the magnetic field would distort the very atoms in your body, because chemistry itself stops working in a field that strong. In 2004, a single magnetar on the far side of our galaxy, 50,000 light-years away, released a flare. For a fraction of a second, that one flicker outshone the entire Milky Way in gamma rays, and it physically compressed Earth's upper atmosphere from half a galaxy away. We marked it. We measured it. And it came from an object the size of a town. So we know the outside remarkably well. We have weighed neutron stars by watching them orbit each other. NASA's NICA instrument on the space station has mapped hotspots on their surfaces to pin down their size. We are good at the outside. Here is where the honesty begins. Go inward. Below the crust, the neutrons are packed so tightly they flow without friction. A frictionless neutron superfluid. That alone is astonishing. A liquid that, once stirred, never stops. We see hints of it when a pulsar suddenly speeds up in a glitch, as if something inside slipped. But keep going. Go to the very center, where the pressure is highest in the known universe, outside of a black hole. And here, physics runs out of road. We genuinely do not know what matter does under that much pressure. One possibility, the neutrons themselves get crushed so hard that they dissolve into their building blocks, free quarks, forming a state called quark matter that exists nowhere else. Another, stranger idea, that the core converts into something called strange matter, a substance that, in some models, would be more stable than ordinary matter itself. We cannot recreate these pressures in any laboratory. We cannot see through a neutron star. So the center remains right now one of the most honest blank spaces in physics. And that is the part worth sitting with. We have an object we can weigh to a fraction of a percent, time to the millisecond, and locate across the galaxy. And we still cannot tell you what its heart is made of. Not because we are lazy, because the answer lives at a pressure the universe only builds in a handful of places, and never where we can reach. In 2017, we got our closest look yet. 2 neutron stars spiraling into each other finally collided, and we felt it. The collision sent a ripple through space-time itself, a gravitational wave that washed over Earth and was caught by detectors built to sense a shift smaller than the width of a proton. In the light from that crash, we saw heavy elements being forged, gold, platinum, flung out into space. The same kind of event, long ago, made the gold that exists on Earth. Some of it is probably on your hand right now. So what's really inside a neutron star? Honestly, a crust of crushed iron, a frictionless ocean of neutrons, and at the very center, a question we have not answered. A knot of matter under more pressure than anywhere this side of a black hole. Possibly made of something that has no name on Earth. We could pretend to know. It would make a cleaner story. But the true story is better, that the universe builds an object a city-wide, heavier than the sun, spinning hundreds of times a second, and dares us to figure out its center. We are still working on it, and the fact that we can even ask the question with instruments that feel a ripple thinner than a proton is its own kind of miracle. If you want the honest version of the cosmos, what we know, what we don't, and the difference marked clearly, this channel publishes a new one every week. Subscribe, and we'll go to the next impossible place together. One question before you go. If we could send one probe into a neutron star's core, knowing it would be destroyed, would you push the button? Tell me below.